Hi everybody, this is going to be our note for 5.4, rate of change. So we're going to calculate the slope using slope formula, and we're going to calculate the rate of change for a given problem which includes units. So to review what we learned in 5.3, we know that the slope measures the steepness of a line. And I gave that scenario where we have like a line like this and a line like this, and we know that this is the steeper line. And we also learned in 5.3 that if I wanted to calculate the steepness of a line, I could do this thing with rise over run. And that will tell me how steep the line is. The bigger the number, the more steep the line. The slope is a ratio which compares how much the y variable changes. Again, it's rise to how much the x variable changes. It's run. Sorry, I just wanted to zoom in a little bit so it's a little bit easier to read. So for example 1 here, we're going to calculate the slope for each of the following line segments. Then we're going to write our answer in reduced form. So when we do our division for rise over run, we'll leave it as a fraction. So we'll do it for line AB, BC, and AC. So for AC first, or sorry, AB first, if I do my rise over run, my equation, actually I'm going to write this equation in just for all of them. So for AB, my run here, 1, 2, for it to be below point B. So our run is 2. Our rise is 1, 2, 3. So 3 over 2. And this is in reduced form because I can't reduce this anymore. For BC, my run is 1, 2, 3, 4. And my rise is 1, 2, 3, 4, 5, 6. Which if I reduce this, I get 3 over 2. Then I'll do this for AC. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's 9 over 6, which is the same as reduced 3 over 2. Divide by 3 here. Divide by 2 here. So question part B says place any point or place point D at any point on line AC without calculation. What is the slope of AD? So if I put the slope here, very natural. But anywhere on this line really though, what we can see is no matter what 2 points I choose on this line, to answer this question, the slope of AD will be 3 over 2. The slope will be the same for any 2 points on the line. So no matter what 2 points we have, the slope of this line will always be the same. So points down here, points over here, if we do the rise over run, it'll always be the same slope. So we can see from the above example that any 2 points along a line can be used to calculate the slope of a line. We can use ratios to compare the rates at which 2 quantities change. These comparisons are called rates of change. A rate of change requires units, such as kilometers per hour. So this is the equation we're going to have to get used to. You'll be using this equation for this chapter and next chapter. In the exam for this course, you'll also be using it in grade 10 for a few chapters. You'll also be using it in grade 11, and you'll have to know it for grade 12. So if we understand this equation, we get to know it, it will be very advantageous for us in the future. So we have slope, which again is the steepness of a line. We actually also called this something else before in 5.1 and 5.2. We also call this the constant of variation. But once we get more into the graphing, we'll be calling it more slope, also rate of change. Also the change in the dependent variable divided by the change in the independent variable, which is also the same as saying, well, dependent variables on our graph, they are the y values, and the independent variables are x values. So the change in the y values over the change in the x values. And we show this change by, if I have two different points, the y values subtract each other and the x values subtracting each other. Now, before we get to using that equation, I want to go over what we mean by rate of change. So we've seen rate of change, or you've seen rate of change, probably, in daily life, but we're just going to kind of associate it with what rate of change is now. So as an example, Donovan Bailey once held the world record for the 100-meter race in 1996, in the 1996 Olympic Games. He ran 100 meters in 9.84 seconds. His average speed can be found by dividing the distance by his time. So his average speed is the distance in this race. He ran 100 meters divided by time. He ran that in 9.84 seconds. And if we divide those two, nope, your video is not frozen. I did not have my calculator handy. We get 10.16 meters per second. So Donovan's average speed was 10.16 meters per second. This means on average, he covered a distance of 10.16 meters per 1 second of the race. This is an example of rate of change because it is a rate that refers to the change in distance relative to the change in time. So we've chosen distance and time in this example for rate of change, but rate of change is really just the change of one thing relative to the change in another thing. So there are other things we could find the rate of change for. One we might see is like dollars per hour. That's a rate of change. There's other things like kilometers per hour. Whoop. If you're buying like bulk food at Bulk Barn, like dollars per kilogram or dollars per pound. So there's many other different rates of change that are just comparing one thing, in this case like money, to time or hour, or money to kilograms, or so on and so on. So in this case, we just showed it with distance over time, and that actually just gives us the speed or the average speed. So now we're going to get to an example where we're going to use that slope equation that we learned before. So example 3 here says Mr. Land's car broke down and he has to walk home. For some reason, I just have a feeling when I read that sentence, somebody out there who's viewing this was laughing. But hopefully that's not the case. Anyways, the following graph shows his distance from school to his home. So also, this is a made-up situation. You'll not be able to hopefully detect where I live based on this. So we're going to determine the slope of this linear relationship using the slope formula and 2 points that are shown. So these are the 2 points that we have. So I'm just going to write them down over here. So we have our first point, and just going from left to right, the first point I see is 2 and 1/16, and then 6 and 3/48. So these are 2 points we're going to be using. So our slope here, our slope equation is y2 minus y1 over x2 minus x1. So now we'll get to see, well, what do we mean by 1 and 2 here and 1 and 2 here? Remember, these are not exponents. So I'm just going to put that here. Not an exponent. So please do not treat it like an exponent. It's not y squared. This is a subscript. The 2 is below the letter, not above it like an exponent. And this just refers to which coordinate we're talking about. So before I start picking which one's the first one, which one's the second one, let's just remember how the coordinates work. So the first number refers to the x value, and the second number is the y value. And I'm just going to label both of these, x and y, just to remember, well, it's x and then y. So this is I'll pick one of these now to be our first point. I'm going to choose this one. I could choose this one, but I'm just going to choose this one. This will be our first point, so it's going to be x1 and then y1. So this has to be our second point, x2, y2. So now I just need to substitute these values into the equation and then use BEDMAS to solve. So we're going to get y2 is 348 minus y1, which is 116. And then we'll divide this by x2, which is 6, minus x1, which is 2. So now, like we did in our review, so again, we're seeing more things that we've done in the past kind of showing up again. We have to treat like there's invisible brackets on the numerators and denominators here. So I'm going to subtract the numerators. I get 348 minus 116 is 232 divided by 4. And now I can try and reduce this fraction if I can, or do division if it's a whole number. So this actually divides into it. I get 58. So 58 is our slope. And if this wasn't like a whole number, we might have a fraction as our slope. That's okay. So yeah, so what are the units of the slope? Hint, consider the units of the numerator and the denominator. So our numerator was distance, was our dependent variable, which is meters. And our time was on the independent variable, the x value, so hours. So our slope here is also in meters per hours, or meters per 1 hour. So that's why we have to consider the unit of the numerator hour. So our units are meters per hour. So in this case, meters per hour, that slope represents speed. That's why we also refer to slope as rate of change, because we see here in this example, by calculating the slope, based on what our units were, we were actually calculating the speed in the situation. So let's get to another example. So example 4 says Ryan was driving a car at a constant speed on the DVP, the Don Valley Parkway. He noticed that after driving for 1 hour, he had 48 liters of gas left. Then, after driving for a total of 3 hours, he had 24 liters of gas left. Assume in this problem that there is a linear relationship between the amount of gasoline left and the time Ryan has been driving. So we're going to express the information given in this problem as two ordered pairs, where the independent variable is time and the dependent variable is liters of gasoline left. So if I had to write two coordinates as time to liters of gas left, based on this question, I can make 2 points. Well, I have time here. At 1 hour, he had this much liters of gas left. 1 hour, 48 liters. And then at 3 hours, there's 24 liters of gas left. So time to liters. We can use these 2 points to calculate the slope of the line connecting these. So we're going to include the units in our answer as well. So remember, I'm going to first label x and y, and then label x and y here. Then I'll pick one of these points to be the first one, and one of them to be the second point. So normally I pick this one, so I'm going to choose the other one this time. This will be our first point. This will be our second point. And even if I switch it again, I'll get the same answer. So it doesn't matter which one you choose to be the first one. So our equation again is y2 minus y1 over x2 minus x1. I'll substitute the numbers in now. Y2 is 48 minus y1 is 24 divided by x2 is 1, x1 is 3. Subtract the numerator and the denominator, so 48 minus 24 is also 24. which is divided by -2. And then I can simplify this. I'm going to get -12. And what were our units? Well, we were doing liters because that's our dependent variable. And we were doing time in hours. So this is -12 liters per hour. So we have a negative slope here. And does that make sense in this situation? Well, we're talking about the amount of liters of gas in the car. So you'd imagine that the longer that Ryan is driving for, the longer the time, the more liters of gas that is being used up. So it kind of makes sense that we're going to be losing liters of gas per hour. So how long after he started driving will Ryan run out of gasoline? Assuming the rate you calculated in part B does not change. So we're always assuming that the car is losing 12 liters of gas per hour. So there's a few ways we can answer this, but I'm going to show this more with a table just so we can kind of see how this rate of change is working. So if I had a table of values here where we had x, which again is the time in hours, and then y, which is the amount in liters. And if I had like these points here, like 148 is here, and then 3 is 24. Well, remember our rate of change is -12 here, or -12, which means if I'm at 48, I must go down 12. Oops, sorry. I must subtract 12 to get to the next value here. And this is per 1 hour. So for 1 hour, it's going to go down 12 liters. And then at 3 hours, I said, well, it's going to be 24 liters, and 36 minus 24 is also 12. So we can keep going with this pattern. If anything, we can actually go the opposite way to help us out. Well, how much did the tank start with? Well, what minus 12 gives me 48, or 40 plus 12, because we're doing opposite operations, will give me 60. So at 0 hours, there's 60 liters in the tank. So then we can go in like this with a rate of change of minus 12 more liters, which is 12. And then hour 5, we're going to subtract 12 again, and we get 0. So we can say, therefore, at 5 hours, Ryan will run out of gas. So how's another way we can solve this? Well, based on this, we can actually make an equation that we can apply for any hour that we want. So if I have my equation, remember, well, first we should check what kind of variation is happening here. Do we have direct or partial variation here? So we have to look at what happens at x equals 0. If it starts at the origin, it's direct variation, but in this example, it starts at 0, 60, so that is partial variation. So remember our equation for partial variation, y equals mx plus b. Well, b we said is our initial value, which in this case is 60, because that's what happened at 0. And m is that constant of variation, which is also the slope, or the rate of change. So we calculate that to be minus 12. So we can actually put in this equation the slope, and put in our initial value, and now I have an equation for this. So if I wanted to find it at 3 hours, and I didn't have the chart, I didn't make this chart, at 3 hours, we're going to just substitute x equal to 3 plus 60. We're going to follow our bed mass. So y is equal to this multiply this, negative 36 plus 60. And then when I add these integers, negative 36 plus 60, I'm going to get positive 24, which is what I get over here. So we can say that when x is equal to 3, y is equal to 24 as a coordinate. So another way we can solve for this. So let's get to example 5 here. The graph below shows the volume of gasoline remaining in a car's tank. We're going to calculate the slope of the graph and interpret the slope as rate of change. So here is the graph. So I zoomed in on the graph just to make an important point here, that when we're given a graph, sometimes it might be hard to kind of see which points we should be using when we're calculating the slope. So I'd say if you can't tell for sure what the point is, then you shouldn't choose it. You should only choose points that will give us, whole numbers or numbers that are easy to calculate with. So for example, like an easy one for me that I see is kind of where we start from. At x equals 0, we have a point between 60 and 70. So it looks like we have a point at 0, 65. That's one point I can use. And remember, for a slope, we just need any 2 points. And any 2 points on the line will give us the slope. That's what we did at the very beginning. So I would choose another easy point. So like at 100, I can see it kind of goes here, but I don't know what this point is on the y-axis. It could be like 51 or 52, or it could be like 50, 2.5. It could be any one of these numbers, so I'm not going to choose this one. Another easy one might be like at 200. It seems to match up to 40 pretty well. And I could probably draw a line here. I can see, yeah, the line's up 40, so I could use another point of 240. Like at 300, you could see that. Again, it's kind of just below this 30 line, so I don't want to really choose that one. I don't want to round my numbers just to kind of make them work. I want to choose points that are very clearly whole numbers or that are easy to work with. So don't put like, don't just say, oh, this is pretty close to that. It should be right on the line, hopefully. At 400, same thing. It's kind of in the middle. I don't really know what the y value is, so I'm not going to use it. And the last one, this seems to be right in the middle. So like we could say at 500, we have 5. So we should be able to choose any 2 of these points, and we'll use them to calculate the slope. So I'm just going to zoom back out. So I'm going to choose the first point and the last point, because I think they were, and just in case I wasn't exact enough with this, these 2 I'm pretty certain of. So I have 0, 65, and 500, 5. And I'm going to label this X and Y, X and Y. Pick one of them to the first point. I'll choose this one. This is the second one. Then I'll get my slope equation. And do you have to write this out every time? Yes, you do. So we're going to substitute our points in. Y2 goes over here, 5. Y1, 65. X2 is 500. X1 is 0. I want to go right downwards, but I don't have space. I'm going to go this way. So 5 minus 65, this is going to be negative 60. If you're not sure, you can double check on your calculator. Over 500. And then I'm going to do 60 over 500, or negative 60 over 500, sorry. We can reduce this to negative 3 over 25. And we can leave it like that as a slope, but if we want to find this as a rate of change, then I can give this as a decimal if I want to. Over 25 as a decimal, we can rate this as 0.12. And since we're calculating liters and kilometers here, this is the units where the dependent variable goes on the top, liters, and then the independent variable goes on the bottom. So liters per kilometer. So the rate of change is 0.12 liters per kilometer. So here's when we can use it as a decimal. But this is we can say these are both the slope. And when we're talking about slope, I prefer the fraction. For rate of change, it's okay for us to kind of use a decimal if we need to. So the next example here just has us practicing that slope equation again. So it says over the time interval given, calculate the rate of change for each variable. Remember, this rate of change also refers to slope, so we're going to be using that slope equation. So we can make 2 points from this first example. At 3 weeks old, a corn plant is 4 centimeters tall. At 15 weeks, it is 46 centimeters tall. So we could do time, again, time because that's our independent variable, to height, which is our y value. So time is the x value, height is the y value. So as one coordinate, we have 3 weeks old and 4 centimeters tall, and then 15 weeks and 46 centimeters tall. So x, y, x, y. We'll pick this one to be our first one, this one to be our second one, and then use my slope equation again. y2 minus y1, x2 minus x1. So again, common mistake I see is people treat these as exponents, so then they put the numbers into the equation, let's say. y2 is 46 minus 4 over 15 minus 3. And then they'll keep the 2 here thinking this is an exponent, putting the exponent here and putting a 2 up here. Then they'll square the number, and they won't square this one because they think it's an exponent of 1, and they just get an answer that's very off. So please do not think that that's an exponent. Remember, that just refers to the second point that we're using. So it's just 46 minus 4 there. So I keep going and just follow BIDMAS, brackets, do numerators and denominators first, and then divide. So we get 42 over 12. 42 divided by 12, I get 7 over 2. And if I were to divide this and put this as a decimal, I would get 3.5. And since we're doing, dependent variable is height in centimeters, and then our time is weeks. So it's 3.5 centimeters per 1 week. So that is the rate of change for this growing corn plant. Our next example, after driving for 4 hours, Tom is 82 kilometers from home, and after driving for 7 hours, Tom is 224 kilometers from home. So same thing, we're going to kind of define what our variables are. Time, we see, so that's going to be our independent variable, x, and distance, it seems like, will be our y value. So we're going to rate our 2 points again. 4 hours, 82 kilometers, 7 hours, 224 kilometers. So another mistake that I'll go through that I see fairly often is sometimes whether the student doesn't know or not, sometimes they're going very fast during a test or a quiz, or maybe they're not paying attention, but they'll do this. They'll put x1, x2, y1, y2. And then they'll just subtract these and subtract these ones. So that is incorrect. So please do not do that. If you turn the video off, that's a very bad place to do that because you're going to miss this part where I say don't do that. That's why I always say label it x and y first, just to remember that it goes x and y. Like another example is sometimes a student will put a y first, they'll put yx, yx. It's happened, I've seen it before. So that's why, remember, it was an alphabetical order, xy, then xy, and then I'm going to pick one of them to be my first point, this one, and one of them to be my second point, this one. So I'll get my equation. And again, the order doesn't matter. If this was first and this was second, I'll get the same answer. So y2 is 82 minus y1, which is 224, divided by x2, which is 4, and x1, which is 7. 82 minus 224 is negative 142, divided by, negative 3. So negative 142 over negative 3. And I cannot reduce this anymore. So if we're doing rate of change here for kilometers per hour, for his average speed, I would do 142 just divided by 3, and I would get 47.33 kilometers per hour. So again, just make sure you label these correctly, x, y, x, y. Pick one of them to be your first and second point, and then just substitute them correctly. One thing we didn't get to an example is what if I had like a negative one? I think it's going to come up later, but just in case. If I had like 1, -2, -3, -4, let's say. If I'm putting that in my slope equation, this is why we had to go over integers and multiplying and adding integers. If I have to put my values in here, this is, let's say, x1, y1, x2, y2. When I substitute y2 here, it's going to be -4. And then when y1 is here, it's -2, but the subtraction sign is still part of the equation. So it's going to be -4 minus -2 over -3 minus 1. So then when we continue here, got to zoom out a bit, or move up, we have to remember that these two negatives are going to form a positive. And then -3 minus 1 is going to be -4. So we have to understand and be able to calculate these integers in order to, do this work. So again, you have your calculator. If you want to type this in your calculator just to double check, or just to make yourself more confident, be like, yeah, this is the right answer. I'm certain of it. Then please just double check on a calculator, and make sure you input the numbers correctly and be careful of the signs. Okay, our last one is about unit conversions. So unit conversions are, well, one extremely important skill for both mathematics and science is the ability to change from one set of units to another. All of these changes are done by multiplying by the rate that one unit changes compared to another. So for this question, we're trying to convert rates of, in this case, kilometers per second, and we want to change it to meters per hour. So how can we do this? Well, it's actually a little bit of fractions, and it's a little bit of units, and knowing what our unit conversions are. So we're going to start with our first set of units, which is kilometer per second, per 1 second, let's say. And then we're trying to get to meters per 1 hour. So the part about fractions, I don't want to scare people, but I want us to understand the idea that if we have like 4x is equal to 8, how do we solve for x here? Well, we divide by 4. And when we divide by 4, 4 divided by 4 just gives us 1x. And I do the same to the side, so I'm going to get 2. But I want to understand this idea, that if I have the same thing on the top and the bottom here, these can cancel out. And we say they cancel out because 4 divided by 4 is just 1. So it just becomes 0. 4 divided by 4 is 1. And we say it cancels out because it's like the number goes away, because anything times 1 is just itself. So it's just going to be x equals 2 here. So this is the part of fractions that I want us to kind of remember in this opposite operation. So we have, in our case, 402.5 kilometers, and I want to figure out and compare it to this number, meters per hour. So if this is kilometers per second, I want to compare it by changing this to meters per hour, and then we'll compare the numbers to see which one is faster. We could also turn this to kilometers per second, and I can do that afterwards. So we know our rates here, our rate of change, kilometers per second, meters per hour. So now I just have to multiply them by their conversion rates. So if I want to go from kilometers to meters, well, how many kilometers are there in a meter? Well, there are 1,000 meters in 1 kilometer. So I want to put this conversion rate, or this the kind of ratio, into our equation here to convert it from here to here. So I'm going to have it as a fraction, and I'm going to have the units of either meters over kilometers or kilometers over meter. So this is important because I want it to cancel out the units. So I see there's kilometers on the top here. I want kilometers on the bottom here, because when I multiply these, it'll be kilometers over kilometers, and they'll divide out to give me 1. They'll cancel out. So we can say 1 kilometer is equal to 1,000 meters. So again, when these cancel out, the units that'll be left over is meters. So then I want to do the same thing for time, seconds. And how many seconds in an hour? Well, 1 hour is equal to 60 minutes. And there's 60 seconds in a minute. So 60 times 60 is going to be 3,600 seconds. So our conversion rate is going to be 1 hour is equal to this. So now I want to get to hours, and I want to cancel out seconds. So I want the same thing here. I want it so that when I start multiplying everything, that seconds here will cancel out any other seconds that's over here. So if seconds on the bottom here, I'm going to put seconds on the top, and then hours on the bottom. So 1 hour is 3,600 seconds. So now when I multiply all of these, remember our units, I have 1 on the top and the bottom, they'll cancel out. I have seconds here and seconds here, so they'll cancel out, again, on the top and bottom parts of the fractions. And the only things I have left are meters and hours. So when I multiply all of these, I'm going to get a very large number. And I'm just calculating it to make sure that I didn't make a mistake. And it's such a large number, I'm going to move this unit over. And we're going to get 1,449,000,000. And then that's it. Sorry, I made it seem like there's going to be more numbers there. So this many meters per hour. So this is so many times more than this one, and I could just divide these two numbers. But the main thing is this unit conversion, and I think it might be a bit confusing. So we're not going to see too much of this, but it is an important skill that we'll need for math and for sure for science. So that's it for the video. Thanks for your time, and try some of the homework.